it's hard to get it started. Once it's going, the cogging torque goes away, but it's part of the feature of what's required to make it work. Frequency of operation, a specific winding technique, and physical placement of the coils are all important, and they all work together to produce the results that you're seeing.
And for terms of the next part of what we're doing, we don't need to understand this part, but it's just the questions that come up when you say the specific winding technique. What is the difference in the winding?
Okay. So this is the core out of a car alternator. Okay. You can see how it's wound. Okay. It's pretty simple. This is a Regenexx coil, and it's wound extremely tight, and it's very symmetrical. So this coil has a lot more impedance than that one does.
Because of wire length?
No, because of the way it's wound. If you took this coil, okay, it's in a radio antenna. It's called parasitic capacitance. Okay. What we're doing is we're using the parasitic capacitance of an extremely tightly wound coil. We're using that to our advantage. If you took this coil and wound it, like this inductor, like you wound it with gaps in it, this would cease to function as a Regenexx coil. It would operate like a regular coil. So
What that reminds me of is a solenoid body. Does that make sense?
well, what it should remind you of is what it should remind you of if you it's your early stages here, okay? So if you put DC into that coil, okay, if they had the same resistance, they had the same number of turns, okay, but if one was wound like that and one was wound like this, if you put DC into it, it takes 5 time constants for the current to reach its maximum in the coil because of the impedance in the coil, okay? 5 time constants.
For which one?
Both.
Okay.
Okay, and the time constant is L over R. So that's the inductance divided by the resistance. If the resistance is the same, but the inductance is different, then the time constant is going to vary. It's going to be short, okay, and here it's going to be long.
Is that to create a phase delay?
To create the delay that you're seeing on the oscilloscope. Now, the time constant is also frequency based. So, like, again, we're way past where we should be at this point, but nevertheless, this is the equivalent circuit for an inductor, okay? DC resistance, inductance, and parasitic capacitance. In that coil, that inductor, this is always negligible, okay? And in this, as the frequency rises, this becomes more and more paramount, okay? The parasitic capacitance of the coil goes from negligible at low frequencies to dictating the function of the coil. And so this coil, when it's operating above the critical minimum frequency, below the critical minimum frequency, it's operating as an inductor, okay? And it's producing a magnetic field around it pretty much at the same time as it's being excited by the rotating magnetic field. Okay, that's the conventional coil. But as you get up above the critical minimum frequency, now this coil, because the impedance, total impedance, which is 2 pi FL plus the DC resistance of the coil, as the F goes up, the total impedance of the coil goes up. As the total impedance goes up, the current carrying capacity of that coil goes down. So and once you get to a point where
Is it the current carrying capacity or just the current?
well, the ability of the coil to allow current to flow in.
Right, yeah.
Okay, the time constant is too long to allow the current to build up to its normal level, like it would if it was a conventional coil. So the current can't build in the coil like it would in that at the same rate. Now this is operating like a multi-parallel plate capacitor where the windings are mini capacitors across and through. That's why if you take it, so each plate, each winding is a plate of a capacitor, okay? And so above the critical minimum frequency, this is storing energy internally in the electrostatic field. An inductor, on the other hand, is storing energy externally in the electromagnetic field.
Right.
That's the difference between the conventional coil, that one, and a Regenexx coil. The time delay that this produces, the load current time delay, is due to the several factors. The winding, again, if we took this and just undid it and wound it like we were drunk and we were winding it, we didn't care, it would cease to function, completely cease to function.
Okay, as you go up in frequency, does the delay stay the same, or is it
No, it
change?
gets bigger.
Okay,
It
so,
gets bigger. And that's why you saw on the oscilloscope,
mhm,
you saw 45 to 50 degree time delay.
yeah,
Okay, bear in mind that both loads are the same, and bear in mind that both coils are being excited by the same rotating magnetic field at the same time, but one of them is, the current is flowing in a different time domain. It's flowing later than the other one.
mhm,
And because it's flowing later, it's not resisting, let's say, the North Pole magnetic, or the South Pole that's coming to it. It's accelerating the North Pole departure while simultaneously attracting the South Pole. That's where the reversal of operation comes from.
so what happens on the other 180 degrees up phase? Doesn't it act the opposite? Like, are you
Yeah.
not getting it pushing back?
Yeah, no,
Instead of accelerating?
here's exactly what happens. So, again, the conventional coil's load current delay establishes the relative position of the magnet as it's approaching the coil at top dead center, okay? So, here we have a North Pole magnet approaching, and at top dead center, that's where the magnet is neither approaching nor receding from the coil's core. Then as it moves away, so as it's approaching, the coil is producing a North Pole that's resisting the magnet's approach. When it's moving away, the coil is producing a South Pole.
Right,
The Regenexx coil produces a North Pole up to this point,
mhm,
but the current level is low. It's at the lowest point. Beyond here, what we have is a North Pole magnet that's moving away from the coil's core. Okay? And we know that because the conventional coil's sine wave establishes that. But the Regenexx coil is still, from here to here, it's still producing a North Pole repelling, accelerating magnetic field on the rotor magnet up to this point, which is, and also down, and then the cycle repeats, where at the lower end, there's a small amount of, let's call it regenerative braking, but the overall effect is, rather than counter torque here, counter torque here, counter torque here, here we have complementary torque. Complementary electromagnetic torque. And
So the complementary is outweighing
boom,
the counter.
that's it. In this prototype, we have the conventional coil producing a counter torque, and we have the Regenexx coil producing a complementary torque. Because the Regenexx coil is a little bit more powerful than the conventional coil, we get acceleration. Now, this prototype is early stage, very early stage.
So in this analysis, you're just looking at the one small part of the entire.
Yeah, in this analysis, all we care about is what's the net effect.
Okay, so but what about the rest of the waveform? Like, what happens? Like, what I guess what I'm asking is, you get this complementary effect
Yeah,
up there, but what about the rest of the waveform?
yeah,
Is it being
it's repeated but reversed. It's repeated but reversed, that's all.
okay? Now, and as you increase.
Okay, go ahead.